Hello friends. So today we are going to solve questions from the year 2001. So in the first question, it says that two particles A and B of masses MA and MB respectively having the same charge are moving in the plane. The uniform magnetic field exists perpendicular to this plane. The speeds of the particles are VA and VB respectively, and the trajectories are shown in the figure. Then we have to find out what is the relationship of these particles with respect to their mass and velocity. So we are given the figure, and it says that two particles, they are moving in a path which is like a semicircle, and the velocity of particle A is given as VA and the velocity of particle B is given as VB. Okay. And as they are moving in semicircle, so let us say that radius of particle B is our RB and radius of particle A is our RA. So this is our RB. And the magnetic force, as they are moving in a semicircle, or we can also call them a circular motion, we can say the magnetic force is going to provide as a centripetal force. So we start from there only. We say that charged particle moves perpendicular to the uniform magnetic field. Therefore, we can say that magnetic force will be our centripetal force. Centripetal force. Therefore, we can write that the force QVB will be equal to mv square upon r. And here velocity, this cancels out square. So this gives us that our r is equal to mv upon q multiplied by magnetic field. And these two particles are having same charge as well as magnetic field. You can say Q and B is same for both particles. Therefore, we can write that our radius is proportional to mass into velocity. So now we have two particles and we can just modify them according to this particular relation. So we can say for particle A, radius is our RA, mass is MA, and velocity is our VA. So we can write our RA is proportional to MA multiplied by VA. Similarly, we can write for particle B. For particle B, radius is our RA, mass is our, particle B, so it will be RB, mass is MB, and velocity is our VB. So our RB is proportional to our MB and VB. But from the figure, we can say our RA is greater than RB. From figure, we can say our RA is greater than our RB. So we simply substitute. We can write our MA VA is greater than MB VB. So the option which matches this is our MA VB. Option number B is the correct one. Option B is correct. We come to the next question. It says that a coil having n turns is wound tightly in a form of spiral with inner and outer radii A and B respectively. When a current I passes through the coil, the magnetic field at the center is. So in this case, we are given a coil, and you can say that, let us suppose this is the coil, and the current I is passed through the coil, the inner radii, if center is our O, so this is center O, and inner radii is given as A, and outer radii is given as B. So we have to find out what will be the magnetic field at the center of this coil, that is at O. So this is a collection of, you can say, concentric circular loop. Radius varies from A to B. So therefore, we can say each small loop of radius R is going to contribute a small magnetic field dB at the center. You can say that the spiral is a collection of concentric circular loops. Concentric circular loops with the radius A to B. Therefore, we can say that magnetic field at the center of circular loop of radius R carrying a current I. The magnetic field magnetic field at the center of a single circular loop of radius r carrying current I we can write it as dB will be mu naught I upon 2r and multiply by dn, where dn is the number of turns in an infinite, you can say infinitesimal radial thickness dr, where this dn is the number of turns in an infinitesimal radial thickness dr. And if the turns are uniformly distributed from A to B, we can write dn upon dr. We can say if the turns are uniformly distributed from A to B, then dn upon dr will be equal to capital N B minus A. So we can say our dn will be equal to capital N B minus A divided by multiplied by dr. So we substitute this into our magnetic field. So we can write our dB is equal to mu naught I upon 2r and B minus A, and this comes as dr. For total magnetic field, we can integrate from A to B. So total magnetic field integration inner radius to outer radius mu naught I n upon 2r B minus A, and here we have dr. Now it's quite simple. We get this as mu naught I n upon 2 B minus A, and we get this as natural log of r and integration A to B. So our magnetic field B will be equal to mu naught I n 2 B minus A natural log of B upon A. So this is our magnetic field due to a spiral, and the option that are available to us is our option number C is the correct one. Option C is correct. Next question. This was also asked in the year 2001, and it states that a non-planar loop of conducting wire carrying a current I is placed as shown in the figure. Each of the straight section of the loop is the length 2a. The magnetic field due to this loop at a point A0A points in the direction. So we have to find out the, you can say, direction of the magnetic field. In the figure we are given that we have a loop. Let us call this a loop as A, B, C, D, E and F, and it states that each straight section of the loop is of length 2a. So we have FE as 2a, and also AB will be of the length 2a, and the current is flowing along this direction. So we have to find out the, you can say, field at the point P, which is at A0A. It means we have X as A, Y as 0, and Z is also A. So we can just make an approximate, you can say, guess of this point A. So we are going to have our X will be A. So this will be somewhere A, and we can just move vertical. Y will be equal to 0, and Z will be also equal to A. So our Z A will be somewhere here. So we can just make an approximate. This will be our point P. So we have to find out the magnetic field at this point P. Direction, and in this case we can say this entire loop we can divide into two sections. First section we can say as A, B, C, D, and another section we can say as A, D, E, F, because they are both lying in a different plane. Okay. So we start with magnetic field contribution by portions, by a section. Magnetic field contribution by each section. So we start with section 1, which is our A, B, C, D, and this lies in the, you can say, plane XZ. Loop in XZ plane. Okay. So therefore we can say that, one second, no, this is not in the XZ, this is in our XY plane. Okay. XY plane. So we can say this is a loop which is in the horizontal plane. You can say loop lies in a horizontal plane, and point P lies above and to the side of this loop, above and to the side of this loop. So the magnetic field at point P due to the current will point along positive x-axis, okay? Because we have this loop. Let me draw approximate figure here. So this is our loop. We have this is our x-axis and this is our y-axis, and the loop is somewhere here. So this is the loop. Current is flowing in this direction. So we have A, B, C and D. Okay. So we can write that magnetic field at P due to current loop due to this current loop point along positive x-axis, points along positive x direction. Okay. And which basically we can say that it is in plus I direction. Therefore, the magnetic field due to ABCD is in our I direction. Similarly, we can find out the magnetic field due to our second section. Section 2, and that section 2 is our DEFA. DEFA, and this lies in XZ plane, and which basically is in, this is a vertical loop. This is our vertical loop, and the magnetic field in this case will point along plus Z direction. Magnetic field will point along plus Z direction, or we can also in plus K. Therefore, we can say our magnetic field of the loop, that is our DEFA, is in our K direction. So, and it also says that in the question that magnetic because the point P, or we can say these loops are symmetrical about the point P. So because of that, you can say that the magnitude of the magnetic field due to both the portion will be equal. So we can say that magnitude of magnetic field due to both portions will be equal. So we can write that magnetic field because of A, B, C, D will be equal to magnetic field because of D, E, F, A, and net magnetic field net magnetic field B is our B in I direction plus B in K direction, because it is equal, so we can just say this is equal to B. So we come B I plus K, and we need to find out the direction. So we can say the direction of this magnetic field will be our 1 upon square root of 2 I plus K. So the correct answer will be our option number D. Option D is correct. Come to the next question, and it says that a current of 10 ampere flows a closed path in a circuit which is in horizontal plane as shown in the figure. The circuit consists of 8 alternating arcs of radii R1, which is given as 0.08 meter, and R2, which is given as 0.12 meter. Each subtends the same angle at the center. So based on this description, we have two questions. First, it states that find the magnetic field produced by this circuit at the center. Secondly, an infinite long wire carrying a current 10 ampere is passing through the center of above circuit vertically with the direction of current being into the plane of the circuit. What is the force acting on the wire at the center due to the current in the circuit? What is the force acting on the arc AC and the straight segment CD due to the current at the center? So we are given this figure, and it is alternating of the arcs. We have having arc of radius R2 and radius R1. Current is flowing in the circuit is given as I1. And first of all, we have to find out the overall magnetic field that is produced at the center. Let us call this center as O. So we can write the formula that part A, for part A, you can say magnetic field at the center of a circular arc of radius R and current I, and the angle it is making at the center is suppose theta. So we can say magnetic field at the center of a circular arc of radius R, current I, and angle theta. So we can write the B is equal to mu naught I upon 4 pi R multiplied by theta. And it says that in the question it is given, each arc subtends same angle. and there are total, you can say, 8 arcs. So in the question it is given that each arc subtends same angle at the same angle, and there are 8 arcs total. Therefore, we can write our theta, that is angle of each arc, will be equal to total angle divided by 8. So this comes as pi by 4 radians. And the first, okay, so we have 2 arcs, total 4 arcs consisting of 4 set each. First 4 arcs is having a radius r1, another set of arcs is having a radius r2. So we are going to discuss it based on 4 arcs, each set. So we can say magnetic field due to 4 arcs of radius r1 let us call that as b1. b1 will equal to 4, that is the number of arc, and mu naught I upon 4 pi r1 and multiply by angle pi by 4. So this gives us equal to, we have it as pi and pi cancel, and this 4 goes with this 4. So we are left with mu naught I upon 4r1. But r1 is given as 0.08, so we substitute all the values and we can write this as b1 is equal to 4 pi into 10 to the power minus 7. Current is our 10, and this is 4 multiplied by 0.08, and this gives us the magnetic field is close to 3.93 to 10 to the power minus 5 Tesla. Now we find out magnetic field due to 4 arc of radius r2. Magnetic field due to 4 arcs of radius r2. Let us call it as b2. So you can say our b2 will be equal to mu naught I upon 4r2, because once again it will be multiplied by 4, and we here, let me write complete formula first. So we can, this is 4 multiplied by, we have mu naught I upon 4 pi r2 multiplied by pi by 4. So once again 4 pi and pi cancels out, so we get this as mu naught I upon 4r2. We substitute the values, we get this as b2 is equal to 4 pi into 10 to the power minus 7. Current is 10, radius in this case is 0.12, so this comes approximately as 2.62 into 10 to the power minus 5 Tesla. Now we can find out the net magnetic field. Net magnetic field B will be equal to our B1 plus B2. Direction will be same. So we simply add it. We get B is equal to B1 was our 3.93 plus, and it was 2.62 into 10 to the power minus 5, and this comes close to as 6.54 into 10 to the power minus 5 Tesla, and the direction will be into the plane. Directed into the plane. Now in the second part, that is part B, it says that a current carrying conductor, long wire, is passed through the center. So in part B, we are supposed to find out the force. First case we have to find out the force, and then on the arc AC and segment CD. Okay, so we have a CD and arc AC. So in the first part, we are going to find out the force on straight vertical wire at the center. Force on the straight vertical wire at the center. In this case, the wire is vertical, so we can say current is along Z axis. So we can say current in the wire is along Z axis. Therefore, you can say the direction of magnetic field is perpendicular to the wire and symmetric. And we can say that the wire is perfectly aligned with the axis of circular field. We can say that wire is aligned perfectly with the axis of circular field. Therefore, net force will be equal to 0. So this was the first part. Now we find out the force on the arc AC due to the central wire. Second part, force on arc AC due to central wire. And the arc AC is like a, so this is our arc AC, and this is center, and the wire is something like this, straight wire. So we can easily see that the magnetic field due to this you can say straight wire is somewhat tangential to the arc AC. So you can say that magnetic field due to straight wire is tangential to arc AC. And the current in the arc AC is parallel to the field because current is flowing in this direction. Therefore, we can say our L is parallel to magnetic field. So this gives us that force on AC will be equal to 0. And now we can find out the force on the straight segment CD due to the central wire. Third part is our force on straight segment CD due to central wire. So the CD is somewhere like this. So this is our C and D, and we have this center, and the wire is like something like the vertical, and the inner distance of the C is the inner radius R1, and the outer distance from the center is our outer radius, that is our R2. So let us consider, we can say we know the formula that magnetic field at a distance x is given as mu naught I upon 2 pi x. Magnetic field due to wire at a distance x, it is given as B is equal to mu naught I upon 2 pi x. So let us consider a small segment dx on this wire. So we consider a small segment dx, and this segment is at a distance x from the center of the wire. So we consider, you can say that force on a segment of length dx at a distance x, So we can write our df is equal to I dx multiplied by b. We already know the equation for B. So we can write our dF is equal to, we have this is I, B is our mu naught I upon 2 pi x multiplied by dx. And the total force for the entire area R1 to R2. The force F will be equal to integration R1 to R2, and we have this as mu naught I and small I divided by 2 pi x multiplied by dx. Now it's quite simple. Okay, that the force is equal to mu naught I 2 pi and natural log of R2 by R1. And we already know all the values. We substitute it, we get this as 4 pi 10 to the power minus 7, and the current is about 10 as well as 10 divided by 2 pi, and natural log of 0.1 to 0.08. This pi and 2 goes away, and we can just write that the force will be approximately equal to 8.11 into 10 to the power minus 6 Newton. So this is the force on the segment CD. Okay, so let me write, this is our CD, 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 and the direction is vertically downward. Vertically downward. So these were the questions which was asked in the year 2001. So this completes all the questions. Thank you.